Dark matter and dark energy is one of the biggest problems in physics today. So it makes up 95% of all the stuff in the universe, yet people actually have no idea what it really is. So recently there has been a very precise map of the dark matter in the universe. And to talk about this today, we've got Eleonora. She is a recent NYU graduate, and she's going to tell us a little bit about these new results. So, hi, Eleonora.
Hi, everyone. Hi. So today I just want to discuss with you guys a little bit this kind of a big result in for scientists, for astronomers, and astrophysicists. And we're also going to discuss a little bit dark matter and the dark energy survey, which is the project that has led to this huge thing, which is the release of the best ever dark matter map. This is just one of the articles that we're talking about this kind of huge discovery, which happened in May. But just to begin with, what is dark matter? How is dark matter even studied? What is a dark matter map and why do we care? Why does it matter? So ordinary matter makes up only 5% of the universe, meaning that everything we see with our naked eyes, it's only 5% of what the universe is really made up of. And it's a little bit like mind-blowing, I think. Then there's dark energy, which accounts for about 70% of the universe. And dark energy consists, it's what cosmologists hypothesize drive the accelerating expansion of the universe by counteracting the force of gravity. And the last 25% is dark matter, whose gravitational influence binds galaxies together. And we're going to just see this a little bit better in a minute. Why is it called dark matter? Because we can't see it at all. It doesn't emit, reflect, or absorb light or any other type of electromagnetic radiation, such as X-rays or radio waves, which are widely used in astronomy and astrophysics to study stars, stars formations, the universe in general, galaxies, and so on and so forth. But X-rays and radio waves are of no use when it comes to study dark matter. However, scientists have been able to infer dark matter's presence and to study dark matter. So how did they do it? Bottom line, they studied the effects of dark matter on its surroundings. But how exactly? So today I'm just going to briefly talk about 3 ways in which astronomers and astrophysicists were able to get observational evidence for dark matter, but there are many more. I'm just going to mention 3 today. So the first one is through galaxy rotation, through the study of galaxy rotation curves. So what is a rotation curve in the first place? A rotation curve is a plot of the orbital speeds of visible stars and gas in the galaxy versus their radial distance from the galaxy center. So if we look at a picture here of a spiral galaxy, we know that the spiral arms rotates around the galactic center. And we can even see from the picture, so by our naked eyes, that the luminous mass density of a spiral galaxy seems to decrease as we go from the center to the arms, to the outer edges. And so if luminous mass were all the matter that we should take into account, then we could model a spiral galaxy as a model in which we have a mass at the center and little test masses orbiting around them. And so just like, for example, our solar system, we would expect the rotational velocity to decrease as we move away from the center. But the results shown that this is not the case, because what is being observed is rather a flat curve of this radial velocity in relation to the distance from the center, meaning that there's definitely matter there that we're not accounting for, that we're not taking into account when we model the spiral galaxy in this way. And so this was one of the very first ways in which astronomers were able to get observational evidence, because the observations were not matching the theory. Then there's another way, which is by the study of galaxy clusters, which are actually crucial when it comes to study dark matter. because their masses, so the mass of a galaxy cluster, can be estimated in multiple independent ways. And this means that in general, you can carry out two different calculations of the mass of the, like, different calculations of the mass of a cluster, and then at the end you can compare the results and you can account for any difference, and at that point you can reason on what the difference can be there and why there's a difference in the first place. So two of the main ways in which the mass of a galaxy cluster can be calculated is one, from the scatter in radial velocities of the galaxies within a cluster, and two, from the X-rays that are emitted by the hot gas in the clusters. So in a galaxy cluster, we can derive the gravitational mass by measuring the orbital motions of the member of the cluster. So initially, like, we can assume for all the galaxies in a cluster to be roughly at the same distance for us. And so any small spread in the redshift, so in their actual distance from us, can be interpreted as orbital motion around the center of the cluster. And so when astronomers think of a galaxy cluster in this way, so model a cluster in this way, then they actually use this model to calculate the gravitational mass of the cluster. So the first is keeping them together. And then this gravitational mass is then compared with the luminous mass that you get from the calculation of the X-rays emission from the hot gas. So, and then any difference in these two can be accounted for dark matter, or in this way they were able to get a sense of that something was there, like the two calculations were actually matching, and so something was there. And then another way in which they were able to get a sense of the presence of dark matter was through gravitational lensing, which is the phenomenon through which you have a source that is emitting light and you are the observer. And then light is being bended from the mass that is between you and the source that is emitting the light. So scientists found dark matter by looking at the light that was coming from distant galaxies, because often that light was seen to be distorted or bent more than what the foreground matter could account for. So they knew the mass that was between them and the source that was emitting light, so between them and the galaxy, but they actually noticed the light to be way more distorted than it should have been. And so this was a hint of some more matter that was there that they couldn't see, but that was there and that was bending light. And so here you can see it from the image, like this is what gravitational lensing look like. You see all this bending of light that they see. But again, this is I just wanted to mention these three ways, but there are many different other ways in which they were able to get to infer dark matter's presence. So I also want to mention a little bit the Dark Energy Survey, which is the project that has led to the discovery of this new dark matter map. So the Dark Energy Survey is a collaboration of more than 400 scientists from 25 institutions in 7 countries. And it was created to tackle big questions like, what is our universe made of? How is matter distributed? What's the role of dark energy and dark matter in our universe? What role do they play? And for the dark matter map, they use artificial intelligence to analyze images of 226 millions of galaxies in the southern sky. And the survey lasted 6 years, during which they surveyed 5,000 square degrees of sky, which is almost 1/8 of the entire sky. And they catalog hundreds of millions of objects, especially galaxies. And to do this, they used the giant dark energy camera to acquire the photographs that they used to create the map. This camera is located at the Victor Blanco Telescope Dome in Chile, and is one of the most powerful digital cameras in the world. And so the results in the new map was announced on May 27, and the map drew on data from the project's first 3 years, which indeed are 226 million galaxies observed over 345 nights. And so the team said that this let them create the largest and most precise maps yet of the distribution of galaxies in the universe. Because so with the camera, they were actually acquiring the location and the position of multiple objects and galaxies, and then they were taking those photos, and then after that, they were using artificial intelligence to locate dark matter within those objects and in that actually part of the sky. And of course, also the dark matter map. They also were able to create the new dark matter map that you see here in purple, in the context of the southern hemisphere sky. So this is a close up to the map here, which depicts all the dark matter that was detected in the foreground of those galaxies. There have been already lots of papers published, and the results have been analyzed, and some conclusion have been drawn. So let's just look at two of the main implications of these results so far. So the first one is that by looking and studying this map, scientists were able to confirm some of the predictions of what astronomers call the standard cosmological model, which is the simplest model that we have so far that explains what's observed in our universe. Specifically, something that it's in this model is the web-like structure of our universe. And this has been observed also in this map, meaning that dark matter seems to confirm this web-like structure of matter. So this also as well for dark matter, but this has been revealed in past studies in terms of the web-like structure of regular matter, but it was expected to be this way. So according to the model, it was expected that the distribution of matter will be a web-like structure. But another kind of like even a bit more interesting implication of this result is this second implication, because by studying these maps, this new map, scientists found hints that the universe might be a few percent smoother than expected. In essence, it is more spread out than the current best theories predict. And so what they were able to infer from this map is that dark energy seems to be more uniformly distributed than what they were expecting. So, and this is not aligned with the predictions of Einstein general relativity, which actually suggests that dark matter should be more clumpy and less uniformly distributed. And so this is kind of a big deal because so I was looking at some of the videos of some of the authors of the project discussing this, and they were, of course, like kind of more excited about the second implication rather than the first one, because they are already discussing that. I mean, though the evidence is by no means definitive, they might be. So someone said that perhaps we're beginning to see hints of new physics. And one of the main authors, Neil Jeffrey, said that this would correspond to possibly changing the laws of gravity as described by Einstein, because so far, the second implication of these results seems to go against Einstein general relativity. And so in these few videos that I was watching, they were just very excited to carry on the work and to see what this would lead us. It's kind of exciting for someone who's in the field working on dark matter and dark energy. So, wow. Wow. I think it's mind-blowing, and there's so much that we don't know yet. But also, as I mentioned earlier, so this map was drawing on data from the first 3 years of the survey. There are 3 more years of data that haven't been analyzed yet. And so I think this makes it even more exciting for what is to come.
Okay, great. Thank you, Eleonora. Questions?
Another is there
Shout at that computer.
I can bring them back.
No. You gotta shout there. You gotta shout. Okay, go on. Keep it up.
Looking at this thing, looking at the map, it looks like it has a boundary. The whitish aura or something, enveloping the purple black thing. Is that part of what is it exactly? Let me not speculate.
It's the Milky Way, isn't it?
I guess it's Milky Way.
It's the Milky Way.
Be the Milky Way.
Okay, and maybe this is, I'm not sure if you can answer this, but, is AI the best way to do this? And why is AI the best way to work this out? Can't you work it out with some actual equations? Yeah. Yeah, sorry. I thought you would not.
Go for some clean Adobe Illustrator.
No,
I don't know, but
I think you could do it in Photoshop as well.
From what we know on this project, they just had like tons of pictures of the sky to analyze. So, would you suggest another way?
Well, I mean, I don't know.
Information.
Just like everything is being done by AI now. Is it a good idea?
That's another topic.
Okay, that's. I don't mean like the machines are taking over. I just mean like, it seems like the go-to thing for everybody in science now. Did you use AI in your project?
No.
No.
She is biological intelligence.
I have to say I prefer to do like some of the photometry myself. Like with the project that I had, I didn't have to use to do like large computation. It wasn't computational based, it was observation based. So I prefer it that way for now. At least it was for my thesis, my caps. But we'll see.
Maybe the point is that there's so much data that somehow that's more efficient, and then you train it first using certain models, and then you use AI because you don't want to, expend the computational cost. Maybe it's something like that. Does that sound plausible? Marek?
How would I know?
I don't know. You're an AI guy, yeah? Maybe.
I like Adobe Illustrator.
But actually, this is one of the places where we should be testing our quantum computational resources.
Quantum AI
Yeah.
to train
Wait,
dark matter map. Well, it's got a lot of buzzwords in it. I like it.
but we don't have a single qubit in this room. I have a question, but I'm not sure if you can answer that. Does dark matter do anything apart from having mass?
I don't know, but it has mass, and so it bends like space-time. Same as regular matter. Not sure if anyone knows.
Yeah, don't even know what it is.
So 1 kilogram of dark matter is same as 1 kilogram of anything.
Really?
Yeah.
How do you even measure one thing?
Yeah. Well, gravitational lensing, haven't you heard?
Okay. All right.
Pay more attention, Abube. What is best way to start to study dark matter? Can you recommend?
What, like a textbook?
No, I hate textbooks.
Okay.
Something online and recent. Textbooks suck.
I'm not sure if NASA, so on the NASA's website, there's a lot of simulation. Like I saw one for exoplanets, like 3D simulation. I don't know if they have a mapping of this, but as Tim was saying earlier, really we know nothing on dark energy and dark matter. So I'm not even sure if they have something online like a 3D simulation or anything. Something that can be mapped. This is probably the best map so far.
Okay, so thank you very much, Eleonora. It was very interesting. Yeah, so we'll leave it there. And so if you liked this video, then please consider subscribing to our channel, and we will see you next time. Bye.
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 Okay, no, well, that was just for the video, Eleonora.